Welcome back to the fourth part of our second lecture on Introduction to Complex and Algebraic Geometry. So today we are going to discuss how being analytic and holomorphic are essentially equivalent, right? So let's do a quick review. We learned about complex differentiable functions. We learned when a function f defined on some open subset of the set of complex numbers to C is complex differentiable at a point z in its domain if this limit exists, if the limit of f of z plus h minus f of z divided by h when h goes to 0, if this limit exists. If it exists, we would say this function is complex differentiable at z, and we call this limit the derivative or complex derivative of the function at z, right? So this is the notion of complex differentiability. We learned another notion. We would say a function is holomorphic if it satisfies the Cauchy-Riemann equations. So if you write f as u plus iv, we learned this means derivative of u with respect to x is derivative of v with respect to y, and derivative of u with respect to y is equal to derivative of v with respect to x with a minus sign there. We learned there is another way to do this, right? We learned this is essentially equivalent to saying derivative of f with respect to z bar vanishes, right? This was the more compact way to say f is holomorphic. If you've forgotten what this means, I recommend you take a quick look at the previous lecture. Okay, the other thing we learned is that these two notions are equivalent. They're essentially the same. With a little bit assumption about continuity of partial derivatives, these two things are the same. In the previous part, we learned a new definition. We would say a function f is analytic if for any point z naught, for small neighborhood of that, we can express f as an infinite sum of this form, some constants a n times z minus z naught to the power n. If we have such a thing and the right-hand side uniformly converges when z minus z naught is sufficiently small, we would say f is analytic. And then the next thing we wanted to say is that these two notions are essentially equivalent, being analytic and holomorphic. We tried to show analytic implies holomorphic, but there was a gap in our argument. So let's try to resolve that. Let's rewrite the statement. So theorem we like to prove. Suppose f defined on some region U is analytic. Say analytic at some point z naught in U. And then we want to show f is holomorphic at this point. So at this point satisfies the Cauchy-Riemann equation, right? This is what we want to prove. So since f is analytic, it means there is some epsilon, so that on epsilon neighborhood of z naught, we have f is equal to a power series like this. So when the distance between z and z naught is less than epsilon. So for some epsilon, positive epsilon, right? And from this, we want to get to the point to show f is holomorphic. We like to show the partial derivative of f with respect to z bar is 0. This is what we like to do, right? So what we do know is that if we define partial sums up to n, so let's say we look at these sums that they define f, but don't go to infinity, just go up to some n, some large number n, let's say, for any natural number n, we get some functions. Let's denote this with Sn of z. So we have these functions. When n goes to infinity, these functions converge uniformly to f, right? So these partial sums approximate f, and when n goes to infinity, they converge uniformly to f of z. Well, they converge uniformly to f on a neighborhood. So Sn of z would converge to f of z. Now, the point is that these partial sums, they are polynomial. f is not polynomial, but the partial sums are polynomial. F is expressed locally as an infinite sum. And polynomials are holomorphic. Polynomials are holomorphic. So we have a sequence of holomorphic functions converging to f uniformly on a neighborhood of Z0. And we want to argue that f is also holomorphic. Okay, so each Sn is polynomial. So each Sn of Z, which is the sum of these terms that describe f up to some capital, and these are holomorphic, so derivative of Sn of Z with respect to Z bar is equal to 0, right? And if I expand that, it means partial Z bar of the sum n goes to 0 up to n, a n Z minus Z naught to the n is equal to 0. This is what we know. So we know this, we have this. What we like to show, what we want to show. We want to show that derivative of f with respect to Z bar is equal to 0, but f is equal to sigma n from 0 to infinity a n Z minus Z naught to the n. We want to prove this. So the main question is that from the second line, can we get to the third line or not? So can we get from here to here? And you might say, well, let's take limit from both sides and send n to infinity. Limit of 0 is 0. And then limit when n goes to infinity would be this infinite sum. There you go. There we have it. But this is not accurate. And the reason has to do, as previously mentioned, has to the fact that we cannot really swap the order of limit and derivative. This is not trivial in analysis. Yes, this is not regress. This is not necessarily correct. So not necessarily true. So sometimes this is not true. How should we resolve this? So the main idea to go around this, the main idea to give a regress proof is based on a very important theorem, which we are going to use in this course a lot, called Cauchy's integral formula. So what does Cauchy's integral formula say? It says, suppose Z0 is a point in U, right? And suppose you have some positive epsilon. So if you look at a disk centered at Z0 with radius epsilon completely falls inside U. So if this is our complex plane, and this is, say, U, this is Z0, there is some small epsilon that if I look at the disk, the small disk centered at Z0 with radius epsilon, it's completely contained in U. Then for any Z inside this disk, we have the following. So the point is that f of Z can be expressed as an integral. So, or in fact, sum of two integrals. This is what is called Cauchy's integral formula. 1 over 2 pi I integral of f of w over w minus z d of w, where w takes value in boundary of d, plus 1 over 2 pi I integral of f, derivative of f with respect to w bar dw wedge dw bar over the whole disk. Okay, so this formula needs an explanation. This might look a bit scary, but it's not. So let's look at this disk here. The center is Z0, and then it has radius epsilon. Okay, the boundary means this one-dimensional circle, not what is inside, only the red bit. right? Only the boundary. So we are integrating along this real one-dimensional object, along the circle. And here, the variable of the integral is w. We are just replacing z with w, okay? So for any z here, so z can be any point here, not that z is any point in the disk. The value of f at the point z is equal to this integral, and what we're taking integral over is w. So w would be every point on this circle, and we integrate over that. What is dw? So w here is our complex variable, just like z would be x plus iy, and d of w would be dx plus I dy. So remember, in real calculus, we used to take derivative of fx dx from a to b. This is the same. Here we have complex version. So it's dx plus I dy. Okay. The second integral, the integral is not over the one-dimensional boundary. The integral is over the whole two-dimensional disk. So we integrate all over the disk, not just its boundary. Okay. And what is d of w bar is dx minus I dy. Okay, so we are going to look at the product of these two. So we have dx plus I dy, which dx minus I dy. So what would this be? Let's think about this completely formally. So there are some rules to write these things. So dx is 0. So we have dx, it's just by definition 0, minus, well, let's continue here, I dx dy plus I dy dx minus I squared, which is minus 1 dy dy. So there are two rules in working with these forms in integrals. One is that any simple thing like dx wedge dx or dy wedge dy is equal to 0. And the second rule is that dx wedge dy is equal to minus dy wedge dx. So there is a mathematics for these things. At this point, let's just think about this only in formal terms. We just want to do computation. We just want to compute integrals. So we don't care much about what their meaning is. So what we get is that this is 0, this is 0. We kind of swap these two, we get a minus 1. So we get minus 2i dx dy. So going to the previous integral, we can just literally replace this with minus 2i dx dy. What is dx dy? So again, from calculus, remember, if we take integral over a two-dimensional region, we used to have integral of, say, some function x and y, dx dy, the integral over, say, this two-dimensional region A. So this is how we would take integral over two-dimensional regions. Here, the disk itself as a real object is two-dimensional, so it's natural to get dx dy. Okay, and the other thing is that here we have derivative of f with respect to w bar. This is just notation. So if f is holomorphic, remember, if f is holomorphic, if we have f of z, if we take its derivative with respect to z bar, it would be 0. It's just we change the notation. If f is holomorphic, if you write it as a function of w, its derivative with respect to w bar would also be 0. So in particular, Cauchy's integral formula, if we also add the assumption that f is holomorphic, it simplifies. So if we do that, then going back here, the second integral would disappear. So if f is holomorphic, this would be 0. But the theorem is stated for general, say, differentiable or continuous function, even in the real sense. We are not here assuming f is complex differentiable. F being smooth in the real sense is enough. So if f is holomorphic, then f of z would be equal to 1 over 2 pi I, integral over dz naught epsilon, f of w over w minus z dw, right? So the other term would be 0 and would not appear, okay? Now, going back to our big picture, we had the notion of complex differentiable, we had the notion of holomorphic, And now we have the notion of analytic. And we want to show these two are equivalent. And if we do that, we get everything is equivalent to everything. And the point is that being equivalent between holomorphic analytic essentially is based on Cauchy's integral formula. That's the essential ingredient to prove that these two notions are the same. So this is the big picture you have in mind. So in this lecture, we are going to assume Cauchy's integral formula to show these two are the same. In the next lecture, we are going to prove Cauchy's integral formula. Today, we are not going to prove that. Today, we are assumed that as a lemma to prove holomorphic is equal to analytic. Later, we are going to see Cauchy's integral formula itself is essentially an application of Stokes' theorem, which you might have seen a version of it, at least in your calculus course, right? But for now, let's just assume that this is correct and try to show holomorphic and analytic are the same. Okay. Okay, so let's go back to our theorem. F being analytic implies F is holomorphic. This is what we want to prove, right? Okay. So we know F of Z is equal to sigma n equal to 0 to infinity an z minus z naught to the n on a suitable small neighborhood of z naught, right? Okay, and then we defined these partial sums. We said we can look at the sum, but not to infinity, just up to some n, right? So if we look at the partial sum, but before going to infinity, if we just cut it at some n, they are approximating f. They're converging to f when n goes to infinity, but they're not equal to the n, right? But the point is that if we denote this function with Sn of z, the point is that these functions are holomorphic because they are polynomial and polynomials are holomorphic, right? So let's write the Cauchy's integral formula for Sn. What would be Cauchy's integral formula for Sn? We can write it for any function, right? So Cauchy's integral formula tells us that Sn of z is equal to 1 over 2 pi I integral on the boundary of this disk centered at z naught with radius epsilon Sn at another point w minus z and then taking integral over w. The next term would disappear because, well, Sn is holomorphic, right? So we don't have the other term. So we have just this simpler version, right? And this is equal to 1 over 2 pi I. Well, let's rewrite it. Sn is sigma n from 0 to infinity, an. Well, here, instead of w, we have z, w minus z naught to the n. Sorry, this is not, the whole point is that this is not infinite. This is up to n. W minus z dw. This is equal to Sn of z, right? This is the formula we have. Now, what I want to do, I want to take a limit from both sides. So if these two are equal, their limit also should be equal. So I take limit from both sides and send n to infinity. So the left-hand side, just by definition, is f of z, right? These functions as n, when n is equal to infinity, is the function f. The point here is that the limit and the integral, they commute because of the uniform convergence we have. So here the series converges uniformly to the function f. That allows us to swap the order of integral and the limit. Integral, which is over w, and then limit, where n goes to infinity. So sigma an w minus z naught to the n over w minus z. And n goes from 0 to infinity. However, when we take limit, this is, let's rewrite this, n goes to infinity, so n goes from 0 to infinity now. An w minus z naught to the n divided by w minus z dw. But what is this? What is the sum of an w minus z naught to the n from 0 to infinity. This is the definition of f. So what we have here, is equal to f of w. What do we get? We get f of z is equal to, so on the left-hand side, we have f of z. On the right-hand side, we have 1 over 2 pi I integral of f of w over w minus z dw. So therefore, we have what we learned is that f of z is equal to 1 over 2 pi I integral of f of w over w minus z dw. So take a look at this. What is this? This is Cauchy's integral formula, but for holomorphic functions. Well, that doesn't necessarily prove f is holomorphic, but at least it shows us that f satisfies the same property that holomorphic functions satisfy. But still, we don't have, from here, just the fact that the second term did not appear, we can't get f is holomorphic, but we are close. F is holomorphic if its derivative with respect to z bar is equal to 0. Well, let's take derivative with respect to z bar from both sides. There would be derivative with respect to z bar of 1 over 2 pi I integral over d f of w over w minus z dw. But the point is that, well, 1 over 2 pi I is a constant. The derivative wouldn't look at that. But derivative also commutes with integral because derivative is with respect to conjugate of z. The integral is with respect to w. When you're taking derivative and integral with respect to different variables, they do swap, they do commute. There is nothing complicated there, right? So this is equal to derivative with respect to z bar f of w over w minus z dw. But what is this thing inside? You see, when we're taking derivative with respect to z or z bar, it means our variable is z or z bar. It means w is like a constant, right? It's just like when we used to take derivative with respect to x and y. When we take derivative with respect to x, y behaves like a constant. And when we take derivative with respect to y, x is fixed and constant. That's the case here. Here, f of w is like constant because it's in terms of w, also the w here. So they also behave like constants. So this is equal to 1 over 2 pi I integral over this disk. F of w is just a constant coefficient. Derivative with respect to z bar of 1 over w, which is like a constant minus z dw. And I leave this to you maybe as a simple exercise. Derivative of 1 over w minus z with respect to z bar is equal to 0 when w is not equal to z. And it's not because z for us was a point inside this disk, and w, the variable of integral, goes around the boundary. So they can never be equal. This derivative is simple algebra computation to see it's equal to 0. Therefore, the integral is 0. And therefore, derivative of f with respect to z bar is 0, which means f is holomorphic. That's great. This shows that being analytic shows f is holomorphic. And we already know being holomorphic and complex differentiable are the same. Now, think about the converse. Why being holomorphic? Why, if we know f is holomorphic, why does it imply f locally should be given by an infinite sum? Why is this correct? Here we followed Griffiths and Harris' proof to show every analytic function is holomorphic. And we specifically followed their proof because we wanted actually to learn Cauchy's integral formula and see an application of that, because we are going to use that in future. However, can we argue that any analytic function is holomorphic via a simpler method? Is the following thing correct? Can we just say because the partial sums converge to the function f uniformly, we can swap the derivative with respect to z bar and the limit. So the proof would be just one line. Is this correct, or there is something wrong with this?